All right, now we're going to start talking about the absent bit string rule. And this thing definitely takes some work to get used to, but I've got 3 examples to kind of help you get used to using it. All right, so first of all, let me just say what the absent bit string rule actually does. All right, so given an infinite list of bit strings, it produces an infinite list of infinite bit strings. So, and remember from the previous video, you can think of these. Here's an infinite list of infinite bit strings. These are subsets. These are subsets of the natural numbers. Okay, so these are all subsets of the natural numbers. So maybe we should go over that real fast. Okay, so what subset of the natural numbers does this represent? Right, remember 1 means in and 0 means out or not in. Right, so 1 is in, 0 is out. Or I'll write that as not in. Not in. Okay. All right. So remember, this is the first position is tells us about 0. Okay. So let's see. This says 0 is there, 1 is there, 2 is there, 3 is there. Let me just count here real fast. Let's see. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 17 is not in there. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, and so on. Right, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yeah, so 17 wasn't in there. So this first line here, or this first infinite bit string, this represents the infinite subset of the natural numbers that has every number in it except the thing that's represented by that position. Right, that is the number 17. So this first line here, right, this really represents, this is the natural numbers, take away 17. That is a subset of the natural numbers. It has every natural number in it except 17. And similarly, this next one, right, it has every natural number except 18 in it. This is the set that contains everything except the natural number 19, and so on. Okay, so that's the numbers that these all represent. Okay, so here we have infinite. All right, so we're thinking of these as these are subsets of the natural numbers. They're just a way to, we just write them with 0s and 1s to represent them in a convenient way. Okay, now what the absent bit string rule does is it takes given any infinite list of infinite bit strings, it produces an infinite bit string that's not in the list. So the infinite bit string rule will create something that's not in this list. And that's what I'm going to show you in this video, like how it does that. Okay. So basically what's going on, right? So like right here, like this is a general description of a of an infinite list of bit strings. This right here could be 0 or 1, this 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 could be, and so on. This could be a 0 or a 1, that could be a 0 or a 1. See, that's where I say that right there. Right there it says where each of these things, bij, I being the I being the row, j being the column that it's in, is either 0 or 1. But you don't need to worry about rows and columns. That's making it way too complicated. Really just think each of these numbers here is either 0 or 1. And what the infinite bit string rule does is it looks along the diagonal. This is what we call a diagonalization argument. So it looks along the diagonal there. I forget that. Okay, so what it does is it looks along the diagonal. And this is an infinitely large array of strings of zeros and ones. It looks along the diagonal, and if it says, okay, if that is a 0, then I'm going to make that into a 1. If that is a 1, I'm going to make that into a 0. So then that means that whatever thing we're producing here is not equal to that first one. Then it looks along this second one, and it looks at this second one along the diagonal. It says, hey, is that a 0? Okay, if that's a 0, then I'm going to make that into a 1. If that's a 1, then I'm going to make that into a 0. So then this one can't be equal to this, because two bit strings are equal when they have exactly the same things in every position, right? So this one can't be equal to that one because it's not equal in the second position. Then the absent bit string rule goes along and says, okay, well, what's there? If that's a 0, then we make this into a 1. If this is a 1, then we make that into a 0. And so then this can't equal this bit string again. And it does that all the way along the diagonal infinitely often, and therefore it can't be in the list. That's how it produces something that's not in the list. Okay, if you don't quite understand what I'm saying there, if that doesn't entirely make sense, it's really not a big deal, because I'm just setting the stage, and now we will see a number of examples where we use it to compute something. All right. Okay, so let's do that now. Okay, so we'll just go here, and now we will look along this diagonal. Okay, so what we do is first look at this first position here. Now, is that a 0 or a 1? Right, not a trick question here, right? That is a 1. Okay, so my bit string that's not going to be here is going to start with a 0. Okay, now we go to the next one down the diagonal. That one. Is that a 0 or a 1? Hey, that's a 1. All right, so then I'm going to make this a 0 there. Now I want you to see how already this first one cannot equal B, right? It can't equal B because to be equal to B, it would have to have a 0 right there. And it doesn't have a 0 there, it has a 1. Right, so it's not equal to that. All right, so now let's go to the next thing down the diagonal. There. Is that a 0 or a 1? Aha! That is a 1, right? It's a 1, so I'm going to make my b equal to a 0 there. Okay, and now notice, right, that right, it can't be equal to that one, right? Why can't it be equal to the second one? Right, look at this thing right there. That's a 1 and that's a 0. So they can't be equal. To be equal, two bit strings have to have exactly the same ones in exactly the same positions and zeros in exactly the same position. So it can't be equal because it's not equal there. All right. And okay, and I keep forgetting to, I guess I'm one behind. And similarly, we're not equal to that one. Okay. Now let's go on to the fourth position there. There. Okay, is that a 0 or is that a 0 or a 1? Okay, it's a 1, so I'm going to make this into a 0. All right, so now let's find, okay, now we'll go to the next position. Now, how do we find the next position? Okay, so it's along the diagonal, so it's the fifth row, fifth column. It's always at, so now we're in the fifth position here. We're trying to fill in the fifth position, right? Because fifth position, let's see. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we can go and find that. Let's see. So here we are. 1, 2, 3, 4. That one right there. Okay. Is that thing there a 0 or a 1? Oh, it's a 1. Okay. So I'll make this a 0. Okay. Now, moving on to the next one. There. Is that a 0 or a 1? Oh, it's a 1. So I'll make that a 0. I know, you're getting bored. I know you are. Okay. Now you go to there. Is that a 0 or a 1? Oh, it's a 1. Okay. So I'll make this a 0. And you see that over time, right, this b is going to be something that's not in the list. Now, you might be saying, why did I put these zeros along here? I did that so that each of these would be different subsets of the natural numbers. If I just had ones the whole way down in every single position, then I would be having, then my infinite list of subsets of the natural numbers would actually just be a list of one thing, right? Because it would just be all of the subsets of the natural numbers that have everything in them. Right? There's only one of those. So I had to have some way of making them different. That's why I put those zeros in there. But these zeros in here, where I have these zeros here, really I just put those in just so I would have different things. But the point of this one is that what do you produce? You produce the one that's not in there is the one that had the one with all zeros. That represents the empty set. So the empty set is not in our list here. And that's the one that was produced by the absent bit string rule.